We'll just start in 2 or 3 more minutes.
Hello guys, can you hear me?
Yeah.
Yeah, bro.
Okay.
And
So 22
electromagnetism,
people.
and had shown that neither of them cared a hill of beans about the direction of the spin of the particles involved.
Yeah, I think we can wait for another 5 minutes, no?
Yeah, yeah. Akshat, can you keep your screen shared? We'll start in.
Yeah, system.
I think we can start. Okay.
Okay. Am I audible?
Yeah.
Okay, so here we are group 3 presenting our topic, and mine is fundamental forces and the need for force carriers. So I will begin. Yeah, so before starting the topic, I will just want to introduce a little to the standard model. Like I think everybody knows, but just a little. So if you are interested in learning particle physics, one of the key topics we need to understand.
हम अपना ध्यान केवल उस अर्ज यानी तीव्र इच्छा पर
I'm sorry.
Yeah, go ahead.
Yeah, so yeah, I will start again. If you are interested in learning particle physics, one of the key topics we need to understand are the forces that come into play, from walking on the street to launching a rocket into space or sticking a magnet to your refrigerator. Physical forces are all around us, but all the forces that we experience every day can be written down to just 4 fundamental forces, like gravity, electromagnetism force, strong force, and weak force. These are 4 fundamental forces of nature, and they govern everything that happens in the universe. So let's start with gravity first. So gravitational force or gravity is the attraction between two objects that have mass or energy. For example, like dropping a rock from a bridge or a planet orbiting a star. Just a second, guys. Sorry. Am I audible, guys?
Yes,
Hello?
You are audible.
Yeah, sorry. Yeah. So gravity is the attraction between two objects that have mass or energy, like dropping a rock from a bridge or planet orbiting a star, or the moon causing ocean tides. Gravitational force is like a non-contact force, well, because there's no contact between the objects. It is also centripetal because it is directed toward the center of the orbit. Also, you can say that it is most probably the most intuitive and the most familiar of the fundamental forces, but it's also been one of the most challenging to explain. So let's dive into a little bit of history. Isaac Newton was the first to propose the idea of gravity. Uh, it is said to be that he inspired by an apple falling from a tree, but who knows? He described gravity as a little attraction between two objects. He also derived a law for the gravitational force. In his book, he mentioned that the time is universal, that is, there's only one clock ticking for the whole universe. And he also admitted that he was not able to explain how two bodies interact at a distance. So this is the formula given by the Newton. Centuries later, Albert Einstein suggested through his general theory of relativity that gravity is not an attraction or a force. Instead, it's a consequence of object bending space-time. A large object bend works on space-time a bit like how a large ball is placed on a sheet, affects the material, deforming it, and causing the other small objects to fall in the middle. We will not go into details of the mathematics, but here's the Einstein's field equation. And I would like the audience to go and search the meaning and the name of the variables and constants used here. So let's, before moving to the electromagnetic force, let's talk about the gravitons a little. So graviton is a hypothetical quantum of gravity. And people might say, what's a quantum? Well, let's assume it is an elementary particle that mediates the force of gravity. It is considered to be massless and its spin is theorized to be 2. There is no complete quantum field theory of gravitons due to an outstanding mathematical problem with renormalization in general relativity. In string theory, which is believed to be consistent theory of quantum gravity, the graviton is a massless state of fundamental strings. Since it is not yet discovered experimentally, you won't find it in the photos of standard model. To be honest, I don't know what renormalization is, and I request if Vikrant sir is here to explain it in the end of the video. So let's move to the electromagnetic force. The electromagnetic force is also called Lorentz force, which acts between charged particles like negatively charged electron or a positively charged proton. People say that opposite attracts. Well, I don't know about the relationships, but electrical charges surely do. Opposite charge attracts and, well, like same charge repels. The greater charge, the greater the force. And much like gravity, the force can be felt at an infinite distances. Even if the particles are separated by the whole universe, they will still feel the force, though it may be negligible. Well, as its name suggests, indicates actually, the electromagnetic force consists of two parts, the electric force and the magnetic force. At first, physicists described these forces as separate from one another, but researchers later realized that two are the components of the same force. The electrical component acts like It acts between charged particles, whether they are moving or stationary, and it's create a field by which the another charge influence each other. But once the charge is set into motion, those charged particles begin to display the second component, which is the magnetic field. It is shown here. So, example, when the electron zoom through a wire to charge your computer or your phone, or when you turn on your TV, for example, the wire becomes magnetic. It is also called electromagnetic wave, and it is represented like this. So electromagnetic waves are, sorry, electromagnetic force are kind of transferred between charged particles through an exchange of massless force carrying bosons called photons, which are also known as the particle component of light. Well, but there's a but here, because according to University of Tennessee, Knoxville, the force carrying photons that swap between charged particles are, however, a different manifestation of the photons. They are virtual and undetectable, actually, even though they are actually technically the same particles as the real and detectable version. Also, the quantum approach of the electromagnetic force is called quantum electrodynamics. I'm not going into much detail of quantum electrodynamics. So yeah, the electromagnetic force is actually responsible for some of the most commonly experienced phenomena, like friction, as shown here, the normal force, and the force actually holding the solids together in a given shape. It's even responsible for the drag that birds, plane, and even Superman experiences while flying. These actions can occur because of charged particles or even neutralized particles interacting with one another. The normal force that keeps the book on the table is actually a consequence of electrons in the table atoms repelling the electrons in the books. And this equation, F is equals to QE plus QV into B, is called a it shows the force of it shows electromagnetic force, where E vector is electric field and B vector is magnetic field. Now moving on to strong nuclear force, let's dive a little bit into a history. Well, this is something we have known essentially for a century. In 1911, Rutherford discovered the basic structure of atom, which is that it consists of a small dense nuclei and electrons are surrounded by it. And in 1970, he actually discovered proton, which meant that the nucleus is not one blob of electric charge, but a whole bunch of smaller blobs held together. Now let us try to imagine a simple nucleus consisting of just two protons, as shown here. Let's forget about the neutrons for now. Since each proton has a positive electric charge, they push each other. And they don't push each other just a little. Their repulsion force actually said to be about 20 pounds. Well, I know it is not large for us, but in the particle world, it's actually very huge. Well, if you let those protons go, they push until they are moving away at a speed of, I think, over 7,000 or 8,000 miles per second. And I just picked the simplest case of two protons. Just think, in the case of uranium, there are 92 protons packed together in a ridiculously tiny amount of volume. And the proton on the surface is repelled with just over 70-pound force. So if these protons are getting pushed apart from one another, what keeps them together? Well, there's only, I think, one possibility. There has to be a force that is stronger than electromagnetic force. And the name of that force is, the strong force, of course. So what do we know about the strong force? Well, we know that it's strong, but it just can be a little stronger than electromagnetic force, because then the protons will just push away each other. From tests that we have known that the strong force is about 137 times stronger than the electromagnetic force. But the story is a bit trickier than that. After all, if the force is so high, What keeps the strong force from continuing to gather all the protons until the whole universe consists of a big nucleus? Well, the problem is the range. The range of the strong force is actually very less. You can even see in the periodic table that we see that the highest stable element has no more than 100 protons in it. And I know that nuclei also contain neutrons, but that doesn't change much in what we're talking about here. So sorry, where was I? Yeah. So just like electromagnetism has an infinite range, the strong force has very short range. So let's dive a little bit into particle physics, I guess. Yukawa, a scientist, modeled the strong force as an exchange force in which the exchange particles are pions or other heavy particles. The range of the particle exchange force is limited by the uncertainty principle, and I will derive that in the end. Since proton and neutron, which make up the nucleus, are themselves considered to be made up of quarks, just like shown here. And the quarks are considered to be held together by the gluons, which is also called the color force. So the strong force between nucleons, that is the proton and the neutron, is considered to be the residual color force or the residual strong force. Since the individual gluons and quarks are contained within the proton or a neutron, the masses attributed to them cannot be used in the range relationship to predict the range of the force. When something is viewed from like emerging from a proton or a neutron, then it must be at least a quark-antiquark pair. So it is then plausible that the pion as the least meson should serve as a predictor of the maximum range of the strong force between nucleons. Let's move on to the weak nuclear force. So I want to show a little bit of history of it. So I think I will show a bit of a clip of a video. Tell me if it's audible or not. Is it visible? The screen is visible?
Yes,
Yes,
it
it
is.
Okay.
Isn't relevant. So in the 1950s, scientists had tested interactions using both the strong force and electromagnetism and had shown that neither of them cared a hill of beans about the direction of the spin of the particles involved. However, in 1956, two Chinese theoretical physicists, Tseng-Dao Li and Chen Yinyang, dug through the literature and found that nobody had tested whether the weak force cared. Now, neither of these guys knew how to test this because they were, well, theoretical physicists. So they turned to a female experimental colleague by the name of Chen Xingwu. The female thing will be relevant in a moment. Wu was an impressive scientist. She was the best in the business when it came to studying the spin of atomic nuclei. So what she decided to do was to set up an experiment in which cobalt-60 would decay via the weak force into nickel-60, an electron, and an electron antimatter neutrino. In order to test whether the weak force cared about spin and spin directions, Wu had to set up a very strong magnetic field to align the spin of the cobalt nuclei. Spin is one of those things that is conserved, which means that it has to be the same before and after an interaction. The spin of cobalt-60 is 5, and the spin of the form of nickel-60 into which it decays is 4. The spin of both the electron and neutrino is a half. So we can see in this diagram what has to happen in terms of spin. We can even put in some plus signs and an equal sign to really make the point. In terms of the decay, what you'd expect to see is that during the decay, the electron and antineutrino would fly away along the direction of the spin of the cobalt nucleus, or the opposite direction. And if the weak force doesn't care about spin, the electron moving up and antineutrino moving down configuration would occur as often as the electron down and antineutrino up configuration. Because it's very hard to detect neutrinos, she just looked for the direction the electron flew. So what did she see? Well, she saw the most unexpected thing. The electron always flew away in the direction opposite of the spin of the cobalt nucleus. Because momentum is conserved, that meant that the antineutrino always traveled in the other direction. So what did it mean? It meant that the weak force had a preference for certain spin configurations. After some thought and careful study, what we now know is Wu's observation originates from a very peculiar property of the weak force. This feature is the following thing. There is a very strict rule about the spin of neutrinos and the direction they're traveling. The rule is that the spin of a neutrino is opposite the direction the neutrino is traveling, and the spin of antineutrinos is parallel to the direction they're traveling. We physicists have a jargon for this sort of situation using hands. Take both hands and point your thumbs in the direction a particle is moving. If the fingers of your right hand curl in the sense that the particle is spinning, we say that it's a right-handed particle. If the fingers of your left hand curl in the direction of spin, it's a left-handed particle. And you can see here how the right-left-handed jargon is related to the arrow method of labeling motion and spin directions. Okay, now we're ready to talk about what this all means. An incautious individual would say that Wu found that all neutrinos are left-handed and antineutrinos are right-handed. But that would be a hasty statement. The more accurate statement is that since neutrinos are only observed via weak force interactions, we can say that the weak force only interacts with left-handed neutrinos and right-handed antineutrinos. And, generalizing further, the weak force interacts with left-handed particles and right-handed antiparticles. So this is a big deal. The other forces don't care about the handedness of the particles they interact with, but the weak force does. This discovery blindsided the scientific community and required them to entirely rethink the theory of the weak force. It also raises the question of right-handed neutrinos. Do they not exist? Or do they exist, but we just can't see them because the weak force refuses to interact with them? The story of the search for right-handed neutrinos is an interesting one and worth a video in and of itself. If only there was someone with a history of creating videos about particle physics who could make one. And about that female thing. I sketched out the most basic description of Qiansheng Wu's experiment, but the reality was unbelievably subtler and more complex. It was an experimental masterpiece. Plus, the result overturned our understanding of the weak force. If you're a serious student of science history, it's worth looking up. With such an accomplishment, you'd think that she'd be a shoo-in for science's highest honor. And indeed, the 1957 Nobel Prize in Physics was awarded for this line of work to, you got it, Yang and Li. Wu was entirely overlooked. Now, I wasn't on the committee at that time. In fact, I wasn't even born. And maybe the committee had a strong bias for theoretical instead of experimental work. But I can't help wonder if gender didn't play a role. Maybe not, I don't know. But there is no question in my mind that Wu should have received part of that Nobel Prize.
Okay, so this is a little history and information about weak forces. I will just go to the PPT. Yeah, so in addition to that, just wanted to add that the W and Z particles are the force carriers for the weak nuclear force. And I think it is very clear because of the previous lectures. And the discovery of W and Z particles was actually hailed as a confirmation of the theories which connect weak force to the electromagnetic force, that is in electroweak unification. And I will give this as an assignment to go and look up a little bit about electroweak unification. The weak interaction actually acts between both quarks and leptons, whereas the strong force does not act between leptons. And I think it is pretty much clear why it doesn't. Leptons have no color, so they do not participate in the strong interactions. Neutrons have no charge, so they don't experience electromagnetic force. But all of them experience weak interactions. Also, archaeologists use carbon-14 to date ancient bone, wood, and other formerly living artifacts because of weak force. Carbon-14 has 6 protons and 8 neutrons. One of those neutrons decay into a proton, which make a nitrogen-14, which has 7 protons and 7 neutrons. And this decay actually happens at a very predictable rate, which allows scientists to determine how old artifacts are. So this is the summary of all the things. I will share the PPT in the group so you guys can look up it. And I think it's pretty much simple here. Okay, the next topic is the force carrier and the need for force carrier. Actually, you can think of a force carrier as a like messengers which transfers force. Like they are the particles that act like messages exchanged between other particles. And the scientists have actually discovered only 3 of the force carrier, but there are 4 fundamental forces. The 3 of the force carrier are the gluons, W and Z bosons, and photons for the strong force, weak force, and electromagnetism, respectively. Particles can communicate with another in different languages as defined by the kind of force they are carrying. So, but 2 particles can only communicate with one another only if they are exchanging same force carriers, because then only they will convey the same language they both understand. For example, a charged particle like an electron respond to force carriers to electromagnetic force, but a neutral particle like a neutron does not, because it does not understand that language. Sometimes 2 particles must be very close to communicate with each other via force carriers. Just like example is electron and neutrinos can exchange W bosons, which are force carriers for the weak force, only when they are very close to each other, pretty much touching each other. A force carrier can convey different messages, like protons and electrons, which has opposite charge, are attracted to one another through electromagnetic force. Well, everybody knows that, I think. The particles that carry that force are called photons. They act like love notes. They draw protons and electrons together. But when, in the case of 2 electrons, the photons act more like a hate mail. They actually push electrons apart. Now let's talk about the range of force, which I told I will derive it in the end. The range of force is actually directly related to its force carrier. Well, this is because the force carrier must be emitted from one particle to reach other particle. However, the emitting particle is considered at rest in its own reference frame. Like if consider there are 2 particles and a force carrier is releasing from one particle, then the force carrier is supposed to be at rest from its own reference frame. Emitting of force carrying particles actually violates conservation of mass energy. However, this can be allowed in the uncertainty principle. The amount of energy borrowed multiplied by the time it is borrowed for cannot exceed Planck's constant. So I have written here E is the energy of the force carrier and T is the time energy it is borrowed for. It is T is equals to time the energy is borrowed for, actually. So this is what the principles say, I guess, that E into T should always be less than or equal to H. It cannot exceed Planck's constant, where H is the Planck's constant. Now we write E is equals to mc square, and then we get T is less than equals to H upon mc square. So a maximum distance of force carrier can travel in time is equals to T is equals to D, which is equals to the speed of the force carrier, that is the speed of light, into time. So you can see that the D is pretty much D is less than equal to H upon mc, and this is how the range of the force is defined. Sorry,
Akshat, I have a doubt. Can I?
yeah.
So for the previous equation, right? H by
Bro,
MC.
Yeah.
No, Sagar was he saying something? Should I ask it like after the lecture, or can I ask now?
no, I was actually telling, is that the inequality sign, isn't it wrong? It should be the opposite direction. Like energy into time should be greater than H, isn't it?
Yeah, it should be greater than, first of all.
Oh, yeah. Thank you very much, bro. I think I wrote it wrong.
So your final inequality would have D greater than equal to H over MC. So H over MC is actually what is called the Compton wavelength, right? I don't know if you know about it.
Yeah,
I
that's what.
will correct it, I think, later on, or yeah, I will see it. I will check in a detail about this thing. I'm really sorry.
Yeah, that's it. That's what I want to ask as well.
Yeah.
Oh, and another thing, aren't gluons massless?
Yeah, they are massless. Did I say that they have mass?
No, but what about the H by MC formula then? So what? How do you calculate the range of the strong force?
No, I told you the. I think I explained it that the what about the strong force, that they are actually not measured like this way. They are like I don't know the details, but it says that the pions play a major role in detection of their range.
Okay.
I'm not sure how, but pions are the thing that
Okay. Okay.
predict the
No, you
maximum
said
range.
it, but you also put this formula, so I was confused which one was for what. But okay,
No,
cool.
this is not. I was going to actually say that this is not applicable for the strong force actually.
Oh, okay.
Yeah.
Aratha,
So you-
one more thing. Where is
Yeah.
the factor 4 pi in the denominator?
Where 4 pi?
It should be h by 4 pi. Uncertainty principle. Or
Yeah,
h.
I'm not sure about this. I think I will check it into detail about this. I actually derived it myself from the statement he showed, so I can be wrong totally.
So here, are you taking the mass as the mass of the force carrier? Here M, the rest like.
Yeah, I'm actually. Okay, sorry.
So you're
Actually,
taking the proper mass.
yeah, I'm not sure, but actually I derived it myself, so I was going
So
to say that I
I
can
think
be wrong.
it will not be the rest mass. So I think it should be proper mass only. But still,
It is
if
not
you're
rest
taking,
mass. The rest mass of force carrier is zero. Everybody knows that, but it is like mass. It is proper mass. Yeah.
so that is like the you're using the mass of the force carrier only. Then if this has to make sense, then whatever you're writing, I'm not sure about the theory, but I just wanted to know this M term. You're
Yeah.
using it for what, like for M of the force carrier only, right?
Yeah. It's for force carrier. Yeah.
I have a doubt.
Yeah.
Guys, I think we can keep the doubts in the end. Okay, we can complete the talk first.
Okay.
Okay.
Use chat box. Use chat box.
I'm sorry, I don't know how it came like this. Just let me fix it a little bit. Yeah. So last topic is the need for the force carrier. Well, this is just a part of mechanics of quantum field theory, which is what we get when we integrate standard quantum mechanics with special relativity. Particle is actually really a misnomer in quantum field theory. In quantum field theory, particles are patterns of excitation in space-time filling fields. Actually don't got that, so I'm just stating the line it says. The basic reason is that the theory doesn't allow action at a distance. If something here is going to affect something there, then something has to travel between here and there to mediate that effect. The wave pattern that do what we call force carrier particles. So I would like someone to explain me the first point. I actually got the second point, and thank you pretty much. Now my friend will talk about the bosons and its properties, I guess. Thank you.
Yeah, thank you, Akshay, for a wonderful talk. Now I'm going to talk about the properties of bosons. First, let me share my PPT. Okay, is this PPT visible to all?
Yeah.
Okay. Okay. So let's start with the properties of boson. So first of all, we will understand what exactly means the boson. Okay. So in quantum mechanics, boson are particles which follow Bose-Einstein statistics. Okay. The name boson is given to commemorate the contribution of Satyendranath Bose, which was the Indian physicist and professor of physics at University of Kolkata. Actually, I would like to have some history regarding this, means why we call this as a boson. Okay, so it was actually Bose who actually figured out how a group of identical photons would behave. Okay, so he was interested in reproducing mathematically Planck's law of radiation using only quantum mechanical ideas. Okay, so he employed a technique in this calculation that laid the foundation of quantum statistics. Okay, so this is further known as a Bose-Einstein statistics. Right? So he then sent his paper to Albert Einstein, who recognized the value of his calculation and had the paper translated into German and published in the journal called it is a journal in German language. Okay, I don't know how to produce it. Is Discretes for Physics. Okay, this was the journal. Okay, so this paper turned out a seminal one, and this the technique used by Bose goes under the name Bose-Einstein statistics, and the particles such as photons that obey these statistics are called as bosons. Okay, that was the theory. Means why is called a boson? Because these are nothing but the photons which obey the Bose-Einstein statistics. Therefore, this called as a boson. Okay, so that is the basic history about it. Okay, so now let's identify uh, what are the bosons, and there is one another particles also associated with it. These are the fermions. Okay, if we have a two particle boson and fermion, then how we'll come to know that this is the boson and this is the fermions. Okay, so let's have a look how to identify that. Okay, mathematically. So how to, here in the slide they showed how to differentiate bosons and fermions. So for that, we need a wave function of the particle because we are in the quantum world. Okay, so for to associate or to denote some quantum state of the particle, okay, we need some wave function so that we get the information about it. Okay. So wave functions are like for fermions, it is like this. Okay, that just I'm using the pointer here. So this is a wave function. Okay, this is the wave function of the fermion. Okay, and this is the wave function of boson. As you see that in the fermions there is an up peak and down peak. Okay, so generally we call this is as asymmetric wave function. Okay, because there is no similar symmetricity in that. Okay, but bosons, when we classify this as a boson, then these have a symmetricity like this. It is symmetric about this vertical axis. Okay, so this is called a boson. Okay, just remember that wave function. Then we have some mathematical understanding. Okay, or some mathematical technique to differentiate between boson and a fermions. So this is a fermion look like, and this is a boson wave function look like. Now, this is a one mathematical technique we actually introduce here. So here, let's take one particle which is of xi. This xi a of r. This is a particle A, and this xi b of r is a particle B. Okay, in at a certain distance r. Okay, that certain distance r is nothing but along x-axis, like at 2,0 or at the 6,0. Okay, just assume that. Okay. Now at that position we want some wave function. Okay, so this wave function we can be written as xi of r1 comma xi of r1, and for that second particle it will be xi of, sorry, the phi of, not xi, is phi of r1, and for b particle it is phi of r2. Okay, now since these particles are identical, now the particles are identical means what? They are identical in mass, charge, and spin. Okay, these three things must be identical so that we can say that particle and b particle are identical. Now if you want that particle to be indistinguishable, okay, indistinguishable means what? Like we have some identity, like my name is Manish and some other name, like we have some names. Okay, so we have some identity. But if we don't have any identity, then how we come to know that this is particle and this is particle B? Because in quantum world we know that particle are not find out, means according to Heisenberg uncertainty principle, we can't find the position and momentum at the same time. Okay, so similarly here we can't actually differentiate this is particle A and this is particle B. Okay, so for that we just take this is phi of r and this is phi of b. But here we can't identify its wave function, but we can identify its what we can say probability of this probability distribution function, because we know that in a probability distribution function, when we get a higher p, then at that position we get a higher chances of that particle must be there. Okay, so this is one we can say that the probability distribution function we can use to identify. Okay, so for this particle are indistinguishable, so we can say that the probability distribution function of phi of r1 comma r2 is equal to phi of R2 comma R1 means what? As they are indistinguishable, but they exist at some location. So we can say that there is some peak at some say 6 comma 0, and there is some peaks at 3 comma 0. Okay, there has some peak, so we can say that particle must be there. Okay, so just we take the wave function and that wave function square it, and we will get a probability distribution function. And for the indistribution particle, that probability distribution function must be same. So if we equate this and taking the square root, okay, when taking the square root, then we will get phi of R1 comma R2, which is equal to plus or minus, okay, this plus or plus phi of R1 R2 comma R1, or it is R1 comma R2. Okay, so we get one wave function as phi of R1 comma R2 is equal to phi of R2 comma R1. See here, the coordinates are reversed. Means what? The particle here, there is a possibility that particle A must be going into the rightward direction, and particle B must be going into the leftward direction. Okay, they interchange their position. Okay, so that is this wave function indicate. Okay, so we get this is a positive wave function, this is a negative wave function. Now, if we have some quantum operation on this, okay, to figure out what exactly they have. Okay, so let's have some quantum operation on it. This is phi of s of R1 comma R2. So we will get 1 by root 2 of particle A wave function, particle B wave function, plus particle B wave function at R1 and particle A wave function at R2. Okay, and similarly the below line. Okay, when we have some quantum operation. Okay, so when here you see that here the wave functions are nothing. These are the quantum state. This is xi of A of R1 and xi B of R2. These are the quantum state, because we know that if particle is appear at constant some position, so when we measure it, then the wave function will be collapsed. Okay, but before there can be a multiple state. So we are writing here all multiple states. Okay, so this all multiple state represents the combination of all quantum states when that particle will be measured. Okay, so here when this quantity follows this mathematical operation, then we can say that this function is boson. And when we follow these mathematical operation, then here's the negative sign is. Okay, so this negative sign, when negative sign comes, then it will be fermion. Okay, let's identify if two particles in the same state, like R1 is equal to R2. R1 is equal to R2 means what? They actually at this position. Just I'm using my pen here. Yeah. So particle. So here the particle just at R1 is equal to R2 means at this point we can say at this R is nothing but R1 is equal to R2. So here when we equate, when we put here in that function, in that operation, R1 is equal to R2 here. So we will get here 1 by root 2 of xi that quantum state at R1, quantum state of particle B at R2, quantum state of particle B at R1, and quantum state of particle A at R1. Okay, when we put this and having some mathematical operation, then we will get this is a twice of quantum state of a particle A of whole square and quantum B, quantum state of particle B the whole square. Means what? This is a twice. Means what? This just remember the previous one slide when we show the wave function of the boson. Okay, so when at R1 equal R2, they function come close together, and we will have here this wave function. So okay, this is nothing but this is a twice of the wave function of the boson. Okay, one particle. Okay, because we know that the particle are identical, so we can add easily. Okay, so we get twice of, means there is a maximum peak at this point. So we can say that we actually identify and we get a symmetricity in that. Means this wave function is symmetric about both the axis, this vertical axis. Okay, so we can say that this follows a Bose-Einstein condensation. Okay, any doubt till now? Hello. Okay, so this is the Bose-Einstein condensation formula. Okay, now what about fermions? Because we identified these are the bosons. Okay, with the help of this formula, we are able to know that this is nothing but the bosons. Now, what about fermions? Is there any property? Let's put R1 is equal to R2 in the below function. Okay, because we have to verify this is fermions or not. Okay, so here phi of A R1 comma R1. When we put this value here, then we get a similar quantum state here. Xi R1, Xi B R2 minus Xi B R1, Xi R1. Okay, sorry R1. So all R1 are there, and this is the same, na? Just like 1 minus 1. So we will get a 0. So we can say that we can actually draw it diagrammatically. At this R1 is equal to R2, this is my R. So we will get here one positive P and one negative P, because remember the fermion wave function. Okay, so when we close together, when we come close together at R, then this will be positive and this will be negative. And when we have a measurement, that this will cancel out with each other. Okay, so we will get only, so sorry. So here, when they cancel out each other, we get a 0 wave function at that point. Okay, what exactly measured at this position? Only one particle we can measure here. Okay, so we can say that the probability distribution function is also 0 at this point. Okay, so yes, any question? Okay, so here this is nothing but a Pauli exclusion principle, because it says that there is no possibility that number of particles which are appears to be at the same one quantum state. Okay, bosons can be grouped together in a one quantum state, but fermions they not. They actually arrange in a different orbits or different quantum state, and each quantum state having one fermion. Okay, and the second quantum state there is one fermion, means they can't be grouped together. And this is nothing but a Pauli's exclusion principle. Okay, so this we can actually
Screen is not visible.
yeah, just wait. Now it is visible.
Yes, yes.
Yeah, so this is a Pauli's exclusion principle. Okay, so here we actually distinguish that this is a boson and this is nothing but a fermion. Okay, that is a mathematical technique of wave functions. Now the next one. Now this is the same thing which I was explained here. So interchange, there is an operator P. When we operate on the wave function, it will give the two possibilities, that plus and minus. Okay, so this plus one is a symmetry wave function of boson, and minus one is a antisymmetric wave function, which is nothing but a fermion. For that, we must know that probability distribution function of that particle must be equal. Then and only then we can able to find out. Okay. Now the next part. So it is next is nothing but the properties of boson here. Okay, so let's have some property here. So here properties are nothing but W and Z bosons are nothing but the weak bosons having odd parity. Okay, which mediate the weak interactions. As they said that between the quarks and all these are the strong interaction actually, but weak interaction is what when two particles are very close to each other. Okay, so they have some weak interaction here. So here W boson, this is having a positive charge. Okay, and W minus boson, this is having a negative charge, and there is one boson which is Z0, which is having electrically zero charge. Okay, which is neutral, we can say. Okay, so W plus or minus boson, the two bosons have magnetic moment. Okay, both having a magnetic moment as they having a charge plus and minus, but Z0 has nothing related to magnetic moment because it is electrically neutral. Okay, so all, and we can say that these all three are very short lives. Okay, this is having a very short half life. Okay, about when you can say 3 into 10 to the power minus 25 second. Okay, so they will vanish very quickly. Okay, so they are precious in establishing a standard model of physics. Okay, so we must be encountered that particles. Okay, now second one is W plus or minus bosons are verified mediators of neutrino absorption and emission. Means what? When let's consider there is some particle here, and when neutrino beam is coming out, and when it strikes the particle, okay, so this interaction follows the emission of W plus and minus bosons. Okay, means what? It is actually happening here, the nuclear transmutation. Transmutation means what? There is change of protons and neutrons, okay, inside the atom. Okay, so due to this change of proton neutron, electron will be emitted. Okay, some particle will be emitted and we generally note it as an electron. Okay, and when we find out that electron, then we can say that there is some what we can momentum change occurs. That's why this electron is coming out. Okay, so we can say that these bosons actually imparted some momentum change. Okay, that's why we call this is as a gauge boson. Okay, now second one is a Z boson. What is a Z boson? So the function of Z boson, it mediates transfer of momentum, speed, and energy they, because it is not having any charge. Okay, so it only interacts by transfer of momentum, speed, and energy. Okay, when neutrino scatters elastically from the matter. Okay, what do you mean by elastically scattering? Elastic scattering means what? There must be a charge conservation there. Means no charge is lost during this collision. Okay, or not collision, it is scattering. Okay. Now, let's have some another properties. Like bosons are heavyweights of elementary particles, right? So W bosons have 80.4 giga electron volt per c square. That kind of the mass. Okay, and Z boson have 91.2 giga electron volt per c square. Okay, so we can say that this is a 80 times as massive as the proton. Okay, and photon has a zero mass, we know, and graviton, this is a hypothetical concept actually, but we consider this is have a zero mass. So that all spins have here are one. Okay, so this follow, if this has a zero mass, then all spin will be equal to one. Okay, so the emission of W plus and W minus boson raise or lowers the electric charges of emitting particle by 1 unit. Okay, and also alters spin by 1 unit. And emission of absorption of W plus or minus boson can change type of particle. Okay, changing a strange quark into a what we can say the up quark. Okay, that kind of phenomena happens. Okay, so Z naught is not change electric charges of any particle. Okay, because it is not having any charge here. Okay, so it's only change the speed, momentum, and energy of the other particle. Okay, now, if boson have a decay, okay, if W boson have a decay, then it is decay into leptons or anti-leptons. Okay, which leptons, it is nothing but a charged particle, and anti-leptons, these are the neutral particles. Or it can also decay, okay, it may be decay into quark and anti-quark. Okay, that is a possibility. Now, second one is the Z boson. So if Z boson are decay, okay, then they decay into a fermions and its antiparticle. Okay, so we can say that Z0 boson is a mixture of free symmetry breaking of W0 and B0 boson. Okay, so we can say that Z. So in the moral of the story, Z0 boson is responsible for weak force interaction between the neutrino and electron. Okay, in electromagnetically neutral, right? So that is all about properties of W and Z boson. Now just talking about a vector boson. What is a vector boson? Okay, here in the screen, you see in the Feynman diagram of fusion of two electroweak vector bosons, which is W and Z. Okay, to the scalar Higgs boson, which is process of generation of Higgs boson at the particle accelerator. Okay, so in that particle accelerator, okay, when these W and Z boson are coming together and what we fuse together, okay, the fusion is happening, then it will create a very strong field of the Higgs boson. We will name it as a Higgs boson. Why Higgs boson? Because we actually believe that the masses of each and every particle are coming from this Higgs field when these particles are interact with the Higgs field. Okay, so Higgs field will give the mass to the each and every particle. We believe that. Okay. Now, what is the vector boson here? So this name arises from quantum field theory. The component of such particle spin along any axis has the three types of eigenvalues, we can say. Okay, because in quantum state, we generally believe that the each and every particle must have one eigenstate. So that and that eigenstate we have some what we define some quantum states or quantum properties of that material. Okay, sorry, not that particle. Okay, so we must have a quantum state there or some eigenvalues to define this property. Okay, so when we can say that this is having eigenvalues, that these three, it is having three eigenvalues: minus h cross, 0, and h cross. This is h cross is a reduced Planck constant. Okay, so any measurement of its spin can only yield one of these values. Okay, when for when it having a measurement. Okay, when we have a measurement, then we get one of these three eigenvalues. Okay, like h cross 0 or minus h cross. Okay, so it gives the discrete degree of freedom consisting of three states, the same as number of components of a vector. Okay, in the 3D space, like x, y, and z. These are the 3D vector in our 3D space. Okay, so similarly, these eigenvalues actually produces some different bases in the quantum states. Okay, so quantum superposition of these states can be taken such that the transition under notation just like special components of the rotating vector. Okay, so that's why if boson takes to be the quantum of the field is a vector field. Okay, means we can actually define that if boson is coming there. Okay, so we can say that this field must be the vector. Okay, and superposition of all states must be there. Okay, then that's why it is called a vector boson. Okay. And here q in the diagram, q is nothing but some quark particles these are coming. Okay, and from which the w and z bosons are decaying. Okay. Now here I would like to show one video about Higgs boson. Okay, just I will show here. If this video is visible to all?
Yeah, it's visible. You can play it now.
Okay. Just tell me it is audible or not. Is it audible?
No, it's not.
Just
if you have a Zoom settings bar somewhere, I think you'll have an option to share all.
Okay. So I think a co-host can be, I think, Sagar, can you adjust this? Have a look on it.
Actually, Manish, when you are sharing the screen, you'll get an option to share audio.
Okay.
Or better, you can share the link itself. By chance, if it's not possible, you can share the link.
Okay, just a minute. I will figure out. Just give me a minute.
No, stop sharing. Share again. Maybe you'll get an option to share audio.
Okay. Okay, now tell me if it is audible or not. If it is audible? Okay. Just I'm starting from first.
No, it's not audible.
It's audible for us.
All of you, it's audible?
Yeah, it's audible. There's just music.
Is it supposed to be just music or is it supposed to have something else?
No, video and audio, both are there.
There's just music.
Actually, music.
Don't worry.
Music is not important actually. The notice and the information is important.
Yeah,
if
the
music is not
information
audible, then it's okay.
We can only hear the music. We can't hear the information.
No. Only music is there in that audio. Information is only visible. Okay, it is written in the video. Information written in the video. So no one is explaining in the video.
Cool.
Okay, can I play from the first starting?
Yeah, that would be
Yeah,
better.
please.
Yeah. Just I'm playing from the start. Yeah, guys. Have you watched out that video? Hello.
Yeah.
Hello, guys. Yeah. So how was it?
Yeah, it was good.
Yeah, actually,
What's
yeah,
is
actually,
the chance?
Can you share the video actually? Then only we can understand. It's actually
oh,
very fast so that we can just watch it later.
okay. Then I will share the link in the group. Okay, then you guys have a look then. Okay. So in that video, what basically this says that if any particles, okay, so it said that there is a Higgs field which is a scalar field, okay. So when some particles, okay, are having an interaction with the Higgs field, the Higgs field will give masses of each and every particle. Okay, like we can say that the W and Z bosons, okay, the graviton, which is hypothetically, but just we are assume that this graviton is exists. Then there are multiple particles like electron, photon, not photon, sorry, proton. Okay, so all these particles getting mass from the Higgs field when they have an interaction with the Higgs field. Okay, so here, just I would like to share the PPT again here. So we will look at this PPT. The Higgs boson explained in simple terms here. Means what? Uh, when we have it is a molecule. Okay, we know that everything it is matter is made up of molecules. Okay, so inside the molecules there is an atom. This is having some what we can say proton, electrons, okay, nucleus inside the atom. Okay, so inside the nucleus, we know that all protons and neutrons are there, and we know that the neutrons are and protons are made up of some quarks. Okay. So we are actually dividing that molecule into atom, atom into nucleus, nucleus into protons. Okay, protons, quarks, quarks into some energy. Okay, so this energy is nothing but a Higgs boson. Okay, when we there was a theory for this problem that researcher let protons crash into each other in a large hadron collider. By this crash, little particles become measurable, and these were called as a Higgs boson. Okay, some high energy. Okay, high energy particles are there. Okay, so that energy particles are coming from what? Okay, so we don't know the energy source of these particles. Okay, so here the Higgs actually there is a scientist or Higgs. They actually come to know that that particle might be coming from the some scalar field. Okay, some another particle which is they named as a Higgs boson. Okay, these particles are coming from this. Okay, so now there is one question again. Is Higgs boson is a one particle or this Higgs boson is coming from another particle? Okay, so origin of the Higgs boson we also don't know. We know that all particles coming from Higgs boson, but what is the origin of Higgs boson? That is that is unanswered here. Okay, so that is a assignment I'm giving to all of you to figure out is there any origin of the Higgs boson or not. Okay. Now the second one, the next slide. Yeah, there is a the questions we have discussed here about the Higgs boson. This is the hunt of the what is the Higgs boson. Okay, so guys, please have a look on this. Okay, and actually we can say that this Higgs boson also have a relation with the dark matter and dark energy. Okay, because this is a new particle and we don't know anything about it, so we can say that this is related to dark matter or dark energy. Okay, so some research is we want on that. Okay, so that we will get an idea of how Higgs boson coming from, what is the origin of it. Okay, yeah, and there are some questions I have to you all guys. Okay, so now first question is when energy increases. Okay, when energy increases, why all fundamental forces become unified at some particular energy level? Okay, so this is the one question because during that transition, okay, we don't know what is happening, but at the end we know that all the fundamental forces like uh, weak force, electromagnetic force, okay, strong nuclear force, and gravity all become one unified. Okay, so what is the transition? What is happening in between the transition? Okay, that is a one question. And second question is why we need a supersymmetry concept to elaborate about standard model. Okay, for that, I would like to explain some supersymmetry here. So in the supersymmetry, why we use a symmetry? So in symmetry between the spins of a forces and which is not in the standard model. Okay, the spins of the forces which is not in the standard model. A standard model only has some fermions matter. Okay, so here and fermions and bosonic forces here. Okay, so symmetry requires them be a supersymmetry partner to all particles in periodic system, so called the super partners. Okay, super partners. Okay, so super partners must have different masses correspond to the mass of the particle in the standard model. For example, there must be a what we can say the super symmetric partners are associated along with the what the particles in the standard model. Like for the leptons, there is supersymmetry partner is sleptons. Okay, SLEPTONS. Okay, there might be some supersymmetry partner so that our standard model will be completed. Okay, still standard model is incomplete because there is some what we can say, the energy differences and mass differences is remaining in that model. That's why we can say that the standard model is still incomplete. So we can say that there is a possibility that along with leptons, there must be a supersymmetric partner here, which is leptons along with leptons, quarks. So for the quark, there is a squarks, okay, SQURKS. And for the gauge bosons, there might be a supersymmetric partner of gauge ions. Okay, so if you find all these supersymmetric partners, then there might be, we can complete the standard model of the particle physics. Okay, yeah, guys. So this is all about my presentation, and thank you so much. Is anyone having any question?
We'll keep the question at the end, bro, because we need even another presentation. No.
Okay.
Okay.
Okay. Yeah. Now the another topic, my friend Sasireka will explain. Thank you.
Yeah, let me share the screen. Oh, is my screen visible?
Yeah, visible.
Yeah. So, hi everyone. I'm going to talk about overview of force carriers. Well, before going into force carriers, let's look about some fundamental particles and interactions. Most of us know all this, but just let's recap everything once. So the fundamental particles in our nature are quarks and leptons. And we have 6 different quarks and 6 different leptons, and their respective electric charges are listed in this table. And then the 4 fundamental forces in our nature are like electromagnetic force, strong force, weak force, and gravitational force. And the particles which are used to carry these forces are called bosons. Well, photon is for electromagnetic force, gluon is for strong force, and W plus and W minus and Z0 bosons are for weak forces. And for gravitational force is another particle called gravitons. I guess Akshat actually explained about gravitons in his presentation. So I'm not going to talk about gravitons here. And next is the properties of boson. Well, in bosons, the only charged particles are W plus and W minus bosons, and only the weak bosons have masses, which are respectively 80 and 91. Other particles have 0 mass and 0 charge. And if this table, actually this table describes the fundamental particles and what kind of interactions they undergo. So when 2 quarks come closer, they may interact strongly by exchange of a gluon, or they may interact electromagnetically by an exchange of a photon, or weakly by the exchange of one of the weak bosons. That means quarks can interact both strongly electromagnetically and weakly. But whereas when a quark gets close to an electron or any of the charged leptons, so they can only interact electromagnetically and weakly. It's the same case when both electrons or charged leptons comes closer. But when a neutrino is involved, the only possible interaction is a weak interaction by the exchange of one of the weak bosons. Since the interactions are very different intensity, the strongest one will be the favored among the 2 particles. And weak interaction affects only left-handed particles and right-handed antiparticles. As Akshat showed in his video, that's what they said. And hence, the weak interaction actually depends on particle chirality. So if you look into chirality, an object that cannot be superimposed on its mirror image is said to be chiral, and an object that can be superimposed on its mirror image is said to be achiral. So in the figure, we take mirror image of a screw and a nail. So the screw cannot be superimposed on its mirror image since they have threads with different hardness. And whereas the nail can be superimposed on its mirror image, and so it's called a chiral, and the screw is called chiral. But whereas in particles, we cannot place the particles in front of a mirror to find out if it is chiral or not. So particles are actually represented by wave functions, and so the first coordinate system is actually represented by a wave function depending on space and time coordinates, which is right-handed. And the left-handed coordinate system is represented by a wave function by reversing the space variables like psi of minus x, minus y, minus z, and t. So the right-handed and left-handed nature of particles actually Akshat showed in the video. So that's how it actually works. And neutrino is actually a chiral particle, and only left-handed version is observed in the nature, whereas anti-neutrino is also a chiral particle, and only right-handed version is observed in the nature. So this is kind of a question I want all of you to think. Like the strong and electromagnetic interactions not care about chirality, however, the weak interactions does. So it's good for discussion, and you can think about it as an assignment also. So moving on. There are two kinds of weak interactions actually. One would be the charged weak interaction, which is mediated by the W bosons because they have charges. And then the other one is like neutral weak interaction, which is mediated by Z boson since it's chargeless. And the range of these weak interactions is actually about 10 power minus 17 meters. Well, the charged weak interactions were actually recognized from the start. Beta decay is one of the example of charged weak interactions. I'm going to talk about beta decay in the upcoming slides. Whereas the neutral weak processes were not appreciated until 1958. The Glashow-Weinberg-Salam model will actually include these neutral weak processes as essential ingredients. And their existence was actually confirmed experimentally at CERN in 1973. Well, after this, we have this electroweak theory coming up and all these experiments happening that we'll look into next week. The reasons why these weak neutral interactions were not discovered were like nobody was looking for them, and then they actually tend to be masked by much stronger electromagnetic effects. Like for an example, the Z boson can be exchanged between two electrons, and so does a photon. Like a photon is a massless particle, and so the interaction is really strong. But whereas Z boson has mass 19 times more than the proton, and hence its creation out of nothing is highly impossible, which is what makes a weak interaction weak. That means the probability of exchanging a Z boson is actually less when compared to the probability of exchanging a photon when two electrons actually interact. So also the large mass of boson makes the range of the interaction very short, basically zero, compared to the electromagnetic interactions, which has infinite range. So looking into different processes where these bosons are exchanged, let's look into leptons first. A negative lepton converts into corresponding neutrino with emission of W minus or absorption of a W plus. So it can either be an electron muon or a tau neutron where they convert into their neutrinos while emission of W minus and absorption of W plus. And the next process would be muon decay. Muons are actually unstable elementary particles and are heavier than electrons and neutrinos, but lighter than all other matter particles. So they decay via weak interactions. And the dominant among these two equations is the first one. The muon decays to an electron and an electron antineutrino and a muon neutrino, whereas the anti-muon decays into the corresponding antiparticles. So to your right, you can see the Feynman diagram, which represents this muon decay. And in this muon decay, a W minus boson is exchanged. And in this neutrino electron scattering, a Z boson is actually exchanged, and then there's no charge change between and after the reaction. And then coming to quarks, a quark with charge minus 1/3, which is down strange or bottom quarks, converts into the corresponding quark with charge plus 2/3, like up quark or charm quark or top quark with emission of W minus. And beta decay is actually one of the types of radioactive decays where an unstable nucleus loses energy by radiation. And beta decay occurs in one of the two ways. One being when nucleus emits an electron and an antineutrino in a process that changes a neutron to a proton. And the other being when nucleus emits a positron and a neutrino in a process that changes a proton to a neutron. That's like one is beta plus and one is beta minus decays. And This is the Feynman diagram of the beta decay. So this is a neutron where neutron consists of an up and two down quarks, and a proton consists of an up, down, and an up quark. And hence the interaction, and then the W minus boson is actually exchanged, and then the anti-neutrino and electron neutrino and electrons are formed. Next one is neutrino scattering process. Here, this is just an example of a process where the Z boson is actually exchanged, and the charge is actually not changed. And so, like, where can we find these weak forces in nature? The weak force is actually responsible for the radioactive decay of unstable nuclei. For example, it's beta decay or muon decay. And the slow burning of stars like our sun may not be possible without the weak interactions. And supernova explosions, which create all elements heavier than iron, also depends on just the right strength of neutrino interactions. Thank you.
Very nice presentation, guys. So one piece of advice is please stick to your time limit, okay? I saw Aratha and Manish went 10 minutes extra. Okay, so try maintaining time limit. And one more thing is, if you include videos, please add explanation to that. That is, add your own explanation to that. Okay, let the video run behind, but you should be explaining that. That is one good thing what you can do. And it was pretty informative video. Yeah.
Yeah, Miss, along the video we have to explain, right?
Yeah. And the session was very informative. And if you didn't understand, don't worry, because the next week we'll be doing a very in-depth week full of weak forces only. So our Vikrant will be explaining more of mathematical aspects, and we'll also understand the weak interactions pretty much clearly in the next week. And so I think we have to give the Zoom for the gamma ray people now. Hardik will be explaining about transmission and reflection of electromagnetic waves. So what we can do is, if you have any discussion, please continue it in the Discord now. Okay, have a discussion. It's very good, but please continue it in the Discord. By chance, if you guys had completed within 7 o'clock, we could have a discussion here itself. But we have to give the Zoom for gamma ray people now. So have discussion in our Discord, okay?
Just the thing I want to make clear, like the derivation for the range actually is just h upon 4 pi. Everything else is the same. I just said it's h upon 4 pi. Thank you.
Yeah, so actually it was very good approach actually. See, you can try deriving on your own also.
Yeah, actually the statement actually said only Planck's constant, so I thought only h. That's why.
They use Planck's constant or h by 2 or h bar by 2. They are pretty much different applications. Anything can be used. Okay, so that's all, guys. We can end the meeting now, and please continue the discussion in the Discord. Okay, and I think Vikrant will be explaining about renormalization as Akshat asked in Discord now about renormalization.
Yeah,
yeah, but before we hand it over, if anyone here wants to understand the whole laws of reflection, refraction, how the Snell's law comes in, which is something that you've studied in 12th grade, right? That's something you've obviously studied. But if you want to understand how exactly do electromagnetic waves play a role in that, I would highly recommend that you attend this gamma ray session now after 5 minutes. Yeah, that's what I wanted to say. But if you are not so interested in it, that's totally all right. And I'll probably see you guys on Discord. Whoever is coming up, I'll probably see you on Discord after 5-10 minutes or so.
Neutrino group only, right? We should join the voice channel.
Yeah. Join the big neutrino group thing. If you have the neutrino group, join the neutrino group. Yeah. But if you're interested in attending electromagnetic waves, then yeah, this is a really good thing. You can also learn a bit of electrodynamics here as well, which may or may not come in handy for you in your future work. But it's a fun topic if you're interested. So yeah, I invite Hardik to continue.
Thank you. I can share my screen, right? Okay, I'm the co-host. You can see my screen, right?
Yeah.
Okay. I think we can wait for a few more minutes for people to join.
Yeah, just 2 or 3 minutes.
Shall we start?
Yeah.
Okay. Okay then. Hey guys. So today we will be discussing about reflection and transmission of EM waves. This is a very fun concept to learn, and you can play around with different thought experiments with this. And also, it's a concept useful in selecting the apt materials for detectors involved with EM waves. Unlike Vikrant and Sagar, I don't have a pen tablet, so you have to bear with the presentation. So, okay. Okay, so let's just go over the basics of waves and strings first. Wave is basically a moving disturbance in 1D towards the z direction. The wave equation takes the form shown here. Can I share my Adesh? Can you see my mouse?
Yeah, I can see you.
You can see my mouse, right?
Yeah.
Okay. So in one dimension, in the z direction, this is the wave equation. Wave equation which describes the disturbance motion. And here f of z comma t represents a wave of fixed shape, like a square wave or a triangular wave. Here the wave is moving with speed v. In strings, v is equal to this square root of t over mu, where t is the tension of the string and mu is the mass per unit length of the string. One thing to note here is that v is inversely proportional to mu, and this will be an important point later on. So now f can be any function which satisfies the wave equation, but the most common is the sinusoidal wave function. This is because sinusoidal wave functions are differentiable and continuous. More importantly, any wave function can be represented as the sum of sinusoidal functions in the form of a Fourier series. It is the only wave function to retain its wave shape when being added to another wave of the same frequency. And so it's just easy to work with sinusoidal functions, and that's why it's very common to use. Here, as you know, A is the amplitude, K is the wave number, omega is the angular frequencies, and delta is the phase constant. Now, since the wave function is a sinusoidal function, we can use Euler's formula to get a different formula function. Euler's formula is given here as shown, and you can derive it by just considering the Taylor series of each term here, and you can add it up to get this formula. Since the cosine term here in this formula is a real part, and we want to work with real wave functions, so we'll just be considering the real just the real part of this complex function. The advantage of using this form is that exponential functions are much easier to manipulate, and but don't think that sines and cosines are not useful. When you're dealing with odd and even waves, then you will want to use the sinusoidal form instead of the exponential form. Such situations do arise in quantum mechanics if you study later. Okay, so in this presentation, we will be using this tilde symbol about the symbols to denote a complex function. And here A tilde is just AEI delta, and delta is a phase constant again. So this A tilde just absorbs the delta, and we can just work with K and omega for now. And to get back the actual wave function, we will just get the real part of this complex function. And so yeah, that's it. It's just nothing more complicated about this. It's just convenient notation that we'll be using. Now, before we learn the reflection and transmission of EM waves, it would be helpful if we understood the same concepts in strings, since you later see that the cases are very analogous. Okay, let's consider two strings subject to the same tension, but having different mu, which means different mass per unit length, and so different masses. Let the two strings be connected at z equals 0 here, just for simplification purposes. Let's consider a wave traveling towards the north at z equals 0, and from almost infinity, it's very far off, so you can just consider as negative infinity. Now, since v is related to mu, you will realize that the velocities of the waves in the two strings will be different, and hence we have denoted here v as v1 here and v2 here. Now, we have an incident wave, we have a reflected wave, and we have a transmitted wave. And it's just following the complex notation. Don't get intimidated by the equation. It's just very simple if you actually analyze it. So the incident wave here is in the domain z negative, I mean lesser than 0, which basically does make sense because z is a naught, and so it's traveling from almost negative infinity to 0. Here it's just the usual wave function that we had described a few slides back. The reflected wave here, I misspelled this now. So reflected wave here is the same as the incident wave and in the same domain here. And that's obvious because the reflected and the incident waves will be on the same string. But if you if you notice here, there's a slight difference between the two. You see here k is positive, but k is negative over here. It just means that this wave is traveling in the negative z direction. And okay, it makes sense because it's a reflected wave. For the transmitted wave, it's very similar to the incident wave, except that this wave is in z greater than 0 because it's a transmitted wave, and the k is different because it's a different string. And so now what we'll do is since we have understood the individual waves, we can combine all these three over here to get a net disturbance on the string given by this piecewise function. Yes, the incident and the reflected waves will be added because it is their net influence. There's a net influence over here that disturbs the entire string. So we can add these two. And A here, I mean, AT is the transmitted. So when Z is less than 0, you get these two. And when Z is greater than 0, you get this transmitted. Again, it's just simple, nothing complicated. Okay. Now what we'll do is we'll analyze the boundary conditions at Z equals to 0. I mean, we'll consider, we'll analyze what happens to the wave at the naught. So here, if you see, the displacement just slightly to the left of 0 here must be equal to the displacement to the right of 0. If not, there would be a break between the two strings. So in other words, we can say that the wave function is continuous at z equals to 0. It simply means that there is no break at z equals to 0. Secondly, we can always consider the ideal case of the knot being negligible mass. So the net tension on the knot here must be 0. Otherwise, what will happen is that if there was a net tension over here in the knot from the two strings, then there would be an acceleration in the knot. And since the knot is of negligible mass, we would get almost infinite acceleration. This is better depicted here in this picture. See, in this wave, if this is not, I mean, if this tension are not the same, and not pointing in the same direction, then there will be a force over here. Since there will be a net force, and so since this is of negligible mass, we will get an almost infinite acceleration. And so we can assume that the knot here is just continuous. There is this continuous flow of string 1 to string 2. It's just for mathematical purposes. And so now what you'll realize here is this line over here. You can see that is just like a tangent to this curve. And so the tangent is given by the derivative of f over here. So at z equals to 0. Again, it just we are just expressing the physical influence mathematically. So these two are the boundary conditions. The first is that since the string is continuous, the wave function must be continuous at this knot. The second is that to not cause a to have the to have the net tension to be 0, we must get the first derivative of this f to be continuous at z equals to 0, which means it should be equal. So we got the two necessary boundary conditions from which we will analyze the motion of the waves. I hope you guys understood the physical significance behind the boundary conditions. For this, all this is just the math explaining the physics. And let's apply these boundary conditions on the wave function we had obtained before, this one. Okay, so what was the first boundary condition? That the function on the either sides of the knot must be continuous or equal. Hence, the sum of the functions of the incident and reflect waves must be equal to the transmitted wave at z equals to 0. It is the only way which it can be continuous. And so what you do is you take the sum, you replace z with 0, and then you equate it with this. Then your first boundary condition is satisfied. So what we get here is this: ai plus ar equals to 80. Since z is 0, the exponential functions get cancelled out. Okay, this is from the first boundary condition. From the second boundary condition, we know that we have to differentiate this, and then we need to set it to equal. And so you differentiate this part. You set z equal to 0, z equals 0, z equals 0, and then you equate. So since you're differentiating this, ik1 will come out. Again, minus ik1 will come out here, and ik2 will come out here. And I gets cancelled. And because z equals 0, the exponential terms cancel out. So what you're left with is this equation. So after applying those boundary conditions on the piecewise wave function we had obtained, we get these two equations. So solving, what we get is these two. Now you see these two equations have three variables. So ai, ar, and at. So without knowing one of the variables, you can not get the values of all of the other two. And so now, since we usually work with the incident amplitude, so we will be expressing the reflected and transmitted amplitudes in terms of the incident amplitude. And so after solving these two equations, you get this set of equations. Again, remember, we we always want the real parts. We want to work with the real parts because it defines reality. And so we'll be considering real parts of this one, and these are this is a set of equations which we get. Now let's just analyze some cases. Do you guys have any doubts here? Okay, am I going too fast or is it fine?
Yeah, I have one doubt. So we are like expressing AR and AT in terms of a incident, and we are assuming that a incident is known to us because okay.
Yeah, I mean, when you you know the source of the wave, right?
Yeah.
And so you know the amplitude. All you want to calculate is how much is being reflected back and how much is being transmitted.
Okay. Okay.
Yeah. Okay. So let's continue. Let's consider some cases. Okay. So if the first string is heavier than the second string, which means mu1 is greater than mu2, so v1 will be less than v2. Remember, v is inversely proportional to mu, so v1 will be less than v2. Then we get that the phase constant are equal. So this is mathematically, but what does it mean physically? Well, it just means that the incident wave the reflected wave and the transmitted wave are in phase with each other. So the displacement in the string by each wave are in the same direction, upward direction, or in a negative downward direction if the incident wave is in downward direction. So all the waves are in the same phase. Since the phase constants are equal, the exponential terms here get cancelled, and we get these two equations which we can use to calculate AR and AT, so this should be AT. What about the case when the first string is lighter than the second string, which means that mu1 is lesser than mu2, so v1 is greater than v2? Well, then that would mean that the phase constant of the reflected wave is out of phase with the incident wave by 180 degrees. Again, what does this mean physically? This is just math, but what does it mean physically? Well, it means that the reflected wave comes back to the source flipped 180 degrees in comparison with the other two. This is because of Newton's third law. You see, the wave here at the knot is trying to pull the knot up. Now, from Newton's third law, the knot also is pulling the wave down. Since this second string, we are considering it to be heavier, what will happen is that this would pull the wave more, and so we would get a reflected wave. The wave would be reflected back. And also remember that you can never get a inverted transmitted wave. The only inversion will happen is in reflected waves. Again, this is from Newton's third law. The wave is trying to pull this knot upwards, but because of its heavy mass, the knot is pulling it, is able to easily pull the string downwards, and so we get an inverted wave. When this string is heavier than this, then this would be much easier to lift up, and so this does not have that much momentum, that much force to pull it down to get a reflected wave over here, inverted wave over here. And so in the first case, which we had considered this string to be heavier than this string, we get all the waves to be at phase. The reflected wave is not inverted. But when this is lighter than this one, then we get an inverted wave. You can actually test this out by attaching a string to a heavy string or to a wall, and then make a wave by oscillating your arm. You'll observe that the reflected wave will be flipped 180 degrees. So making the calculations, and then you get these two, and you get these two amplitudes. Now, I had mentioned the wall example. So for such objects, you can consider mu2 to be almost infinite, and then you get that the entire wave is reflected back. That is, AR is 1 and AT is 0. And so, you would not see a rope getting inside the wall, do you? So this is the mathematical interpretation of that. I hope you have understood this concept. If you have any questions, please ask, or we can move on to EM waves. Okay. Okay. So let's consider Maxwell's equation in vacuum with no charge or current. Since last week Vikrant had covered how to solve them to get the wave equations, I will not be covering that here. So we can move ahead, and solving these four equations, we get the wave functions for electric field and magnetic fields, and you'll observe that they are the form of the general wave function. And by the way, this Laplacian, this del squared, is simply the generalization of the partial differentiation we had done in the first slide. It's just generalization, nothing complicated. And so from here we get the velocity of the EM wave, which turns out to be the speed of light. We already studied that last week. Okay, so just like in the string, we can express the electric waves and magnetic waves in complex forms as shown here, where E tilde 0 and B tilde 0 are the complex amplitudes, and omega is Kc. Again, it's the same thing, nothing complicated here. We are just dealing with electric and magnetic fields. Now, if you apply Maxwell's equations to these two, for monochromatic plane waves, you get the following relation between the vector amplitudes of B and E. Or in real terms, you get these two. Monochromatic simply means one color. Mono is one, chroma is color. So monochromatic is just one color. And since color is determined by the frequency, monochromatic waves have the same omega, the angular frequency. Plane waves here mean that the fields involved, the electric and magnetic fields involved, are uniform over every plane perpendicular to the direction of propagation. So that is what these two terms mean here. And we get this one in vector form, and we get this one. So we can represent B naught as in terms of E naught, which is helpful. Okay. So the energy per unit volume in EM field is given as follows. Yeah. I will not be covering that derivation of each equation here because that will take a lot of time. Now, since this is the relation between E and B and E for monochromatic waves, we can say that the electric and magnetic contributions are the same. So half from this, half from that. Okay, the energy flux density or energy per unit area per unit time is given by the Poynting vector here. Note that this is the cross product between E and B. So S is a vector, and this points towards the direction of propagation of the EM wave. Now, since these two are fluctuating over time, we are more interested to know the time average value of S rather than the fluctuating value. And so the average value is given by this one. You can get it if you just perform a simple integration over this. And the average power per unit area transported by an EM wave is called the intensity of the wave, which basically is the magnitude of S. And so this is what the intensity of the EM wave is. Notice here that intensity over here is the proportional to the square of the amplitude of wave. This is an important point, so please remember that. Okay. Now let's study the EM waves in matter. For simplification purposes, we will be considering homogeneous and linear media, which mean that the epsilon and mu value that you see here are not changing. It's constant. So in free charge, in absence of free charge or free current, Maxwell's equation becomes this one. The same thing, except mu naught and epsilon are replaced with mu and epsilon. Similarly, for the velocity of the EM wave, we get this one. And where n is the index of refraction. Again, if in vacuum, epsilon and mu is replaced with epsilon 0 and mu 0, so you get a split. Okay. One thing to note here is that mu and epsilon are greater than mu naught and epsilon naught. So n here, so n is a larger value, so v will be lesser in media, and this is why light waves are move slowly in the media other than vacuum. Okay. And just like in the vacuum case, we can get the energy density, the Poynting vector, and the intensity of the wave. Again, remember that intensity is directly proportional to the square of the amplitude. We can also get it for B magnetic field, because we know that B0 is simply E0 by the velocity. But since E0 is more, electric field is more familiar, we consider electric field. Okay, now that we have considered the basics, we can move on to the topic, reflection and transmission of EM waves. If you have any doubts, please do ask. Okay, we'll first consider the normal incidence. Now, in the string situation, it was one dimension. Hence, the knot or the boundary was just a point. But here the boundary will be a plane, which we assume the xy plane to be. In the string case again, we had two strings with different masses. Remember, mu1 and mu2. But here we have two different media with different mu and epsilon values. Please don't confuse mu of string and mu of EM waves. They are totally different quantities. So here we'll be considering two media with different mu and epsilon values. The angular frequency will be omega, and the wave will travel along the z direction towards the boundary. We will consider the wave to be polarized in the x direction, which basically means that the electric field is oscillating in the x plane only. Remember, this is the x direction over here now. We consider the electric field again because I said it's much more familiar with. So we could have considered magnetic field too, but it's just the convention. Okay. Now, so just like before, we get these equations for the incident, reflected, and transmitted waves for both electric and magnetic fields. It's just the same as in the string case, except we have to consider magnetic field also, but there is no difference. So don't get confused. Since we know B0 is simply E0 by the velocity, so we will be considering B0 in terms of E0. It's easier to manipulate. Also, we are considering vectors here, and so we will need the unit vectors to determine the direction of propagation. And since we are considering the complex number I over here, to not get confused, we will be using the x cap, y cap notation. So this is the incident wave. I hope you guys understood. It's the same as before. For the reflected wave, it's the same again. It's just that again, see, k is negative over here because it's traveling in a negative direction. The whole entire wave is traveling in a negative z direction. One thing to note here is that this here it's positive, however the magnetic field over here is positive, but here it's negative. The velocity is negative, which means the magnetic field gets flipped, and you can see over here magnetic field is pointing towards this direction, but after reflection is pointing in that direction. This also can be explained by the pointing vector. If you take the pointing vector over here, I mean it's just E cross B. So from the right thumb rule you can get the direction over here. Now if you take E cross B over here, the direction will be this side. Okay, so the transmitted wave is similar to the string case, with the wave number being different over here, and the velocity is changed over here. Again, because velocity is dependent on the mu of the media, and so velocity is different. Okay. Again, we will be doing the same thing what we did with the string case. We will be considering the boundary conditions. So at z equals to 0, the combined fields on the left, EI and ER, and EI plus EIR and BI plus BR must be equal to ET plus ET and BT. Again, it's just boundary conditions. This should be in accordance with this general boundary conditions. You can derive these conditions from Maxwell's equations. MIT professor Walter Lewin covers his derivations in these lectures, so you can check them out. It's also available in Griffiths. So if you want to know how these four are derived, you can check the sources out. I will not be covering them here. Okay, so one thing to note here is that since we are considering plane waves, we don't have at normal incidence, we don't have any perpendicular component to the surface, and so these two are just trivial. We can discard them. We will be focusing on only these two conditions, the parallel components. So just like the boundary conditions in the string case, here too, by applying 3 and 4 at z equals 0, we get the following equations. is just the same as before. The terms are a bit different. So this is from the electric field over here, and this comes from the magnetic field. We're just expressing B0 as E0 divided by V. And this looks a bit complicated, so we will simplify and then express the final condition here, where beta is just this term over here. Again, remember V is inversely proportional to the index of refraction, hence N2 is up and 1 is below. Okay. Right. So we can solve those two and get this set of equations, which are the complex reflected and transmitted wave amplitudes in terms of the incident amplitude. Doesn't this set look similar to the string case? In fact, actually, for most media, the mu values are almost the same as the mu value for vacuum, and so we can express beta as the as the ratio of the velocities, since we can cancel out the mu over here, and then we can get these set of equation. And just look at this, it's the exact same of equations we had obtained in a string case. I mean, it's just the amplitudes are just different. And so this is why I wanted to discuss the string case before the EM waves. It'll help you visualize and understand the concept better. And as before, we want to deal with the real amplitudes because we want to work in the real world. And so these are the real amplitudes over here. And if V2 is greater than V1, then so if V2 is greater than V1, then reflected is in phase with, since it's a positive quantity, this will be in phase with the incident. If, however, V1 is greater than V2, the reflected EM wave will be inverted. Okay, now this is in terms of the velocities, but since we work mostly with the indices of refraction, we can express this as index of refraction. I hope you guys are not confused with this. It's the same case as the string case. So in terms of indices of refraction, this is the set of equations that we get for the reflected and the transmitted amplitudes. If we take the ratio of the reflected intensity to the incident intensity, we get this. Remember, the intensity is proportional to the amplitude square. Remember, I'm focusing on this point itself. It's because of this. So we can get this this term R over here, and this is a dimensional constant, which is a reflection coefficient. And so this gives us the percentage or the fraction of reflected waves. Okay, and then similarly for transmitted, we get this one. Do remember that I was actually proportional to epsilon and V. Since we are considering in the transmitted case, there are two different media to be considered. So these two terms will remain. But in the reflected case, since we were just considering one medium, it got cancelled. And so we get R and T over here. Again, T is just the transmission coefficient. It gives us the fraction or percentage of the transmitted wave. Do you guys have any doubts? I hope you guys are understanding the concepts. Am I going too fast? Hello?
I have a doubt. I don't know. I think I missed something, but why do you have, I mean, shouldn't it be EI is equal to transmission?
Sorry?
Sorry, the incident should equal transmission plus reflection, right? Why is it reflection plus incident is transmission? The first boundary condition.
Sorry, where did you?
Okay, go back to the slide.
Oh, when I told that this one equal to this one.
No, go to the equations. Equation. Yeah.
This one.
So it's yeah.
Yeah. So in the string case, remember, it's the same thing actually. We need it to be continuous at this point, at this boundary, because there is no break over here, right? So we need it to be continuous. So this entirety of the fields in the first medium will be equal to the entirety of the field in the second medium. We are just considering the amplitude. The intensity is what you say. Incident is equal to, I mean, reflected plus transmitted. But in the case of amplitudes, as per the boundary conditions, EI plus ER will be equal to ET, just for the continuity.
Okay. Yeah, got it.
Right. Again, in this, we did in the string also.
Yeah.
Okay. Yeah. So this is the reflection coefficient, and this is the transmission coefficient. And so if you notice here, if you add these two, you get 1, and as expected, because you need to conserve energy. And here's a small example. When light passes from air, N1 is 1, and into a glass, N2 is 1.5, you could get R equals 0.04, or like 4%, and T is 96%. So almost everything gets transmitted through, and only a little bit will get reflected back. So we have explained transparency mathematically, but please do note that this is at the surface level. This does not include what happens at the molecular level, which considers the direction of the dipoles in the magnetic fields, and it's another topic for a future discussion. So we can discuss it later if you want. Okay, I hope you are not tired. Just one last topic: the general case of reflection and transmission, the oblique incidence. The normal incidence that we just considered here is just a special case of this oblique incidence. Okay, so a general monochromatic wave in complete general case is represented by these two equations over here. Please don't be intimidated. There is nothing to fret over here. It's just the same thing. Only difference here is that since we are considering the general case, we have the vector k over here, which is a direction vector. So you can see here, this ki is a direction of is representing the direction of the incident wave, and so k is just simply the direction vector, and its magnitude is k, and r is just a general form of z. So since in the normal incidence we are just considering one direction, we had z over here, but now we are considering the general case, so we will be considering the entire r position vector here, and so k dot r is simply the general case of kz, which we were discussing in both the string case and the normal incidence case. So that's it. See, this is just the generalization of the entire cases we had studied. The magnetic field here is expressed as like this. So it's the cross product over here, which we had also obtained while considering the energy. Okay, so this is just generalization. So let's consider an incident wave making an angle theta I, and let the reflected and transmitted wave make angles theta r and theta t. This is the incident wave which I've shown here, and so the reflected wave and the transmitted wave are this one. Again, it's the same thing. There's nothing different over here, just general case. Note that all three waves have the same frequency because it's monochromatic, so same color, same frequency, and so since omega is kV, we get this equality over here: ki v1 equal to kr v1 equal to kt v2, and so from here we can express the ki equal to kr, and this thing we get. This is a really important point and an interesting conclusion we'll make a little bit later. So please keep this in mind. Okay. And then again, at the boundary, we have the following equality. This equality again arises from the boundary conditions, which you can confirm on your own. You can go to Griffiths for this. So if we expand this equality of, we get this equality of the sum. It's nothing complicated, just that we are considering the sum of each component, so x, y, x, y, x, y. And so what you'll notice here, when x is 0, you get this equality, and only the y terms survive, while when y is 0, you get only x terms survive. And this is quite interesting, because now what we can do is we can conclude 3 interesting laws from these cases we have studied. So the first law, the incident, reflected, and transmitted wave vectors form a plane called a plane of incidence. And again, this is because this is equal. So what happens is, if we keep the incident wave in just one plane, suppose we keep it in the x plane, then this entire will be 0. We are not considering the y plane, just the x plane. So all of the waves are in the same plane. Second law comes again. Second law, when y is 0, okay, let's just consider this. When y is 0, we are considering only the x components over here. But what are the x components of the vectors? So in this diagram, you can notice that x in this direction. So the x components are simply the sine theta of the sine of the angles over here. So this x component is the sine of the reflected. This x component is the sine of the incident, and this x component is sine of the transmitted. Remember, this is z direction, this is x direction, perpendicular. So we get, since these are equal, we get this equality over here. K1 sine theta I equal to Kr sine theta R equal to Kt sine theta T. And so again, remember I had told you to keep in mind about the equality of the wave numbers from this one. Since Ki equal to Kr, we can say that theta I equal to theta R. And what is this? It's just a simple law of reflection that we study. Again, for the incident and transmitted waves, again from the equality that we had obtained for the wave numbers, we get this equation. And it's simply the law of refraction, which is the Snell's law. I mean, isn't this just amazing? Without using geometrical optics, without using Huygens principle of wavefronts, we derived the classic 3 laws of optics that we have all learned back in high school, all just using the 4 Maxwell equation and the appropriate boundary condition. Okay, so now I'll be leaving the rest of the derivation of the amplitude and coefficients to you. It's left as an exercise to you. I've just put up the final results here. So these are the amplitudes that you get, where alpha is this term over here. Now, if you express cos theta t as this term, and then you get sine theta t as in this term, this is from the Snell's law. You see that if theta I equal to 0, that means is a normal incidence, this alpha becomes 1. And so we get 1 minus beta or 1 plus beta. We get the same set of equations that we had considered for the normal incidence case. And so we just get them back, and this is how the normal incidence is the special case of the general form. And these are the intensities, II, IR, and IT. Again, the intensity is proportional to the square of the amplitudes. And these are the reflection and transmission coefficients. Yeah. So okay, so this everything that I have just explained over here, it was taken from this book entirely. So you can refer, I think it's chapter 10, or there's an entire chapter on electromagnetic waves. So yeah, that is it for today's presentation. Do you guys have any doubts, or I hope I wasn't too fast. Hello.
Yeah, it was great, dude. It was amazing. Guys, if you have any doubts, you can ask.
I wasn't too fast, I hope.
No, no, it is.
Okay. So if you don't have doubts and if you have doubts later, please do ask in the Discord. I, Sagar, Vikrant will be answering them. So yeah, that's it for today. Do attend tomorrow's sessions, and yeah, the next session we'll have is on Monday. And please do prepare the quiz. Quiz will be on the quizzes.com. So I hope you guys are already done with it. So. Okay, thank you guys. I hope you understood and enjoyed the concepts, because I really did enjoy learning the concepts. So take care and bye.
Thank you.